variables can be thought of as containers in which to store data. So each variable represents a different location in memory, so basically a different address in memory where the data is stored. So variables are typically stored in RAM. So the values stored in variables can be changed throughout runtime. But there's another type of variables, what we call constant variables. So these are stored in flash memory and cannot be changed at runtime. So when we use variables, we need to give them names to distinguish between them. And there's various rules that we must follow. So variable names must start with a letter, A to Z, either upper or lowercase, a number, or an underscore. So these are the only characters we can start a variable name with. And a name cannot contain spaces, commas, or special characters other than underscore. So names are case sensitive, so you need to be careful when you're writing your code. For example, voltage, all lowercase is different, will be a different variable than voltage, with the V being uppercase. So you need to be careful when you're writing the case. And the names also cannot be reserved keywords, because there's certain words what are keywords in C and C++, so things like int, for, while, and other words will come across. We cannot call variables the same as those, because obviously the compiler will get confused when it comes to compiler code. So it's very good practice to use descriptive variable names when you're writing your code. So if you just, A is not very descriptive. So the variable A, we actually might be using that variable to store the area of a circle. So it's much better to use the variable name circle underscore area. So we can see here, we can't leave spaces because that'll, the compiler think that's two separate variable names. So we join the two words together with an underscore. So by using descriptive and relevant names, your code becomes what we call self-documenting. So we can put comments in our code to explain how it works, but you'll find by using sensible variable names and function names, the code just becomes self-documenting, and you can almost just read what it's doing. It's also good practice to develop a coding style and stick with it. So for example here, I've done circle underscore area. So you use this kind of convention of using underscore to join words. Your code will just become easier to read and easier for other people to maintain. So it's good, a good kind of tip as well is to make sure that variable names should be lowercase with underscores. That's generally a style you'll find if you look around at code you see on the internet. This is a very common style. So variable names lowercase joined with underscores. So look at this example here. So we've got some code here. Int 1abc. So here we've created a variable. So this variable name is called 1abc. And we've given it, and because it's an integer, we have to give it an integer value. So here we've assigned the value 5 to it. And again on this next line we've got a variable called underscore cc3, given that the value 6. The next variable x is called x45, and we're given that the value 3. And then I'm going to create a fourth variable, 7gdsd, and the value is going to be given by multiplying all these three together. So we're going to get all these values, multiplying together, and store the result in this variable. And you look at that, and it looks pretty much gibberish. And you can just see, just by using more sensible names. So we now call our first variable length of cuboid. So again, all lowercase, trying the words together with underscores. So the first variable length of cuboid, so we can just see straight away that variable is obviously storing the length of a cuboid. Then we've got the width of the cuboid, height of the cuboid. So when it comes to calculate this last variable, what's representing the volume of the said cuboid, we can see it's just length of cuboid times width times height. So you can see just in this very simple example, fairly contrived example, but having sensible variable names makes your code much easier to follow and debug. So when you're using variables, as well as giving them a decent name, you always have to use the correct type as well. So we call this the type of variable. So the different types of data that typically, because there's different types of data essentially that we use to store in variables. So we need to select the correct variable type to use. So there's three main types we'll come across: integers. So there's 0, 1, 2, 3. Well, if they're signed integers, we can also have -1, -2, -3, and so on. We've got characters and strings. So we saw before, we've got hello world. You might want to store the character C or Y or something like this. And we've also got floating point numbers. So these numbers essentially have got decimal places. So 1.5682, for example. So these are typically the three types of variables. As I've pointed out in this part here, it is important to take account of the sign of the data type, especially, well, mostly for integers. So you can see these are all the different types essentially we've got available to us. So we've got what we call a char. So a char is a character is 8 bits. So each one of these is 1 byte, and we know with 8 bits we can store 0 to 255. This is unsigned. So we have to specify the sign. So if you write unsigned char, you'll be able to store a value 0 to 255 in that variable. Or char is signed by default, and then you can go from -128 to +127. Because you can write this as well. If you create a variable, you can do sign char whatever n equals -128. So you can write like that, but it's not necessary to put signed in. So if you don't include anything in front of char, it becomes signed by default. And we've got shorts. So these are the 16 bits. So each one of these is now 2 bytes. So these gives us the values we can store in there. And ints, 32 bits or 4 bytes. Again, you can see we've got these much bigger ranges now. We've got more bytes of these variables. And we've got long as well. So these are 64. That's not a typo, by the way. That is long. So these are 64 bits. And we can see now you can get these humongous numbers in here. So very large ranges. So depending on how many bits you need. So if you're going to be using char, short, int, or long. It is important as well to specify if you want unsigned. Or if you don't want unsigned, you can just leave. You don't have to put anything in front. Or you can put signed in front, it doesn't matter. So the integer types, these are the floating point types. There's 2 different types. We've got a float, what we call a float, and a double. So a float is also known as a single position floating point number, and that's stored in 32 bits. So again, that's 4 bytes. And how the encoding works, it means we can store a number plus or minus 3.4 times 10 to the plus or minus 38. So we can store massive numbers here, and that's accurate to about 7 decimal places. And then for a double, as you can probably guess, this is now double the position. It's double the number of bits. So the range goes up. So this, to the power of 308. There's probably less atoms in the universe than that. That's now accurate. So it's not really the range what's important. You generally don't need numbers that big or small, but it's the number of decimal places. So we can get, we can go accurate to 16 decimal places. So later in the course, we're going to be using an Mbed development board. So this has got an NXP LPC 1768 microcontroller on it, which in turn has got a 32-bit ARM Cortex M3 core. So because this is a 32-bit machine, you can see the native integer type is an int. So we saw this previous table here, an int was 32 bits. So you imagine you've got your 32-bit buses inside, so it's, the native data type for moving is around, it's 32 bits in parallel. So in your code, you should use ints above other integer types, as that can give better performance. But with the compiler, it's slightly different in terms of the signedness, because we saw in this table here, if you write the name, the data type without any word in front, it's signed. So the data types are signed by default, but that is actually different on the ARM. So char is actually unsigned by default. So that'll be different. So this is what it's like on most compilers, but for on ARM, you have to use it like this. So you just wrote char, that will give you unsigned number 0 to 255, and if you wanted to store negative numbers in a char, you'd have to put signed char in front of it. So that's opposite behavior of what we come across normally, but that's just with the ARM Cortex cores. So before we use a variable, we must declare it using the relevant type. So this is a bit different in some other languages like Python or MATLAB and things like this. You don't have to declare the type of variable, but we do with C. So for example, if you wanted to make a variable called counter, before we can use that in the code, we'd have to declare it. So here, we declared it to be an integer, and then give it a name. And again, you want to make a variable to store a voltage. We know that voltage is going to have, be a decimal number. So we're going to use float for this. So you need to put the data type first, and then the name of the variable. So it's very important to declare a variable before you use it, because otherwise you will get a compile error when you try and compile it. So when you create a variable, that's kind of, it's a reserve in an area in memory, but there's no guarantee that area in memory is going to be empty. I think most compilers do kind of zero it out, but there's no guarantee. So it's good practice just to initialize a variable when we're declaring it. So when we create our variable counter, we'll give it a value 0 just to be on the safe side. It's good practice to do this. And the same with the voltage, for example. I'm going to initialize it to be 0. You don't have to use these numbers. You could use other ones if it works for that particular case. But it's a good idea to initialize them, because just leaving them undeclared like this, at that point, if you then say print out the value of counter, there's no guarantee it's going to be 0. You can't assume it's going to be 0. So it can end up introducing bugs into your code. So it is good practice to initialize variables when declaring them. I just want to mention scope. So the scope of a variable determine which parts of the code can access it. So as you can probably guess, global variables can be accessed globally. So all parts of the code can access global variables. So these will exist for the entire runtime of the program. So when you start running the code, global variables are put into memory, and they stay in memory for the entire duration. And then when the program stops executing, they kind of delete from memory, if you will. But it can be bad practice to use global variables. They do have some useful, they do have some uses, especially for embedded systems. But on the whole, it is bad practice to use global variables, because it's very easy to forget where they're modified. If you've got one single variable, what can be modified in lots of different places, it's very easy to just forget, or it can make it difficult to track down bugs because you're just not sure where this one variable has been modified. So we tend to use local variables where we can. So with a local variable, it can only be accessed within specific functions or blocks of code where they've been declared. And essentially, the scope is determined by the curly braces where the declaration appears. So these curly braces, they mark out what we call a block of code. So when that block is being executed, local variables were kind of created in memory when that block's being executed, and then when it's finished executing, they're removed from the memory. So we'll look at just a couple of examples here. So here we got our main function, int main, and here, and we've got another function. So again, later in the course we'll look at other functions, but in this example here I've just created another function. And here we've got a global variable. So you can see here this variable is declared outside of these. So it's outside of these curly braces, and it's outside of these curly braces. So I've called it G underscore counter because this, if you got to use a global variable, it is a good idea to put G underscore in front of it. So that just means in your code, when you come across a variable that begins with G underscore, you know it's a global variable. So I've created a global variable here, initialize it to 0. So that in the main function, because it's global, it can be accessed inside main. So I've given it now the original the value of 0, and I've now give it a value 1. Then we're going to call this function another function. So the code then it'll execute this, essentially jump to here, and then now again because it's a global variable we can access it in this function. I've now set it the value 2, and then we'll jump back to here, and then now the variable is now got the value of 2. So later on in this function, if you come to use that variable, it will have the value 2. So we'll look now at using local variables, where it's going to limit the scope. So you can see here in this example, so we've got our main function here, and because this local value is declared inside these curly braces, it only exists here. And a local value only, this particular variable only exists in these braces. So we've given it a value 5, and then the code will get to this, it'll jump to this function. So we'll jump down to here, and we can see now we've got this other function. Now inside here, so this can get confusing when you're first learning programming, I've got another variable, and I'll give it the same name as this one here. This doesn't matter, because this is a completely different, even though it's got the same name, it's a completely different variable. It's pointed to a different area in memory, because it's been declared in here, so it only exists within this function. So we've actually got two variables with the same name, but they only exist within the kind of scope that they've been declared. So in this version here, I've set it to the value 9. We'll get to the end of this function, we'll jump back to here, but after this point here, this local value is still equal to 5 because it's referring to this one, what's inside this function. This variable here only exists here. It's got no relevance at all to the main function. So in general, if you can, it's better to use local variables. We just limit the scope to specific functions, just to avoid the situation where you might have a global variable what's getting modified in different places, and it can be hard to keep track of where it's being modified. And if you find a bug related to that variable, you're never quite sure where that bug's been introduced. So in the previous examples, the numbers in the source code are not variables. So instead, they're what we call literals. So this is where we just type in a number. So we're not using variables, we're just literally typing in a number. So we use these to represent fixed values in the source code. And there's different ways of specifying these. We can either use decimal. So this is like this first example. So int w equals 15. This will assign the value 15 to a variable, what we call w. We can also use binary. Note this is only actually in the later versions of the compilers. In earlier compilers we couldn't use binary. So if you want to use binary, you have to put 0b in front of it, and then you can just put your binary number of zeros and ones in. So int x equals 0b1111. We know this value is a binary equivalent of 15, so you know, these two things are equivalent. They'll just get the value, decimal value 15, and store it in those variables. We can also use hexadecimal, so put 0x in front of it, and then we put in the hexadecimal value we want. So again, 0x0f we know is the decimal equivalent. Sorry, is 15 in decimal. So all these three variables will end up having the same value. They'll all have the decimal value 15. And then when we're doing floats or doubles, we can also use scientific notation. So, you know, you could write 0.001, for example, or you can do 1e to the minus 3. So those two are equivalent. So you can use this scientific notation. Makes it much easier when using, you know, either big or small floating point numbers. So when we're using literals, it can be important to specify the type of literal to avoid issues. Now this is particular when we're doing integer division. So for example here, we've got an integer variable called n, and I'll give it the value 10. Now in the next line of code, we're going to do 1 divided by n. So we marked it right, we're going to do 1 divided by 10. And because that's a float, we're going to get 0.1. Well, that won't be the case because n has been defined to be an integer. It's going to do this as an integer verb. 1 divided by 10, well, 1 divided by anything in integers, it can only give us an integer value, so it's going to give us 0. So we need to, the literal needs to be specified as being a floating point number for it to work correctly. So this is one way of doing it. So rather than writing 1 over n, you can write 1.0 over n. So that then the compiler knows you're doing 1.0 over n, so it knows it's a float point number divided by 10, and it's going to give us the correct answer of 0.1. Or you can use 1.0f and do that over n. So this, you know, putting the 0.0 or the 0.0f basically tells the compiler that do a floating point division. So if you don't do it and you end up with just 1 over n, it'll do integer division, and you'll start getting mistakes in.